Okay, so I will do the rest of 11 this chapter 11 this week. So we do the today. So we do the openness first. We have this orbifold with the R and then TNs and so we have some open set and then in the home space and then there's some section defined here. And is going to be the subspace of here with these Rn and Tn determined by these sections and stable reducible normally. So CDEP is the same with the only requiring the uh, convex projective structures and SDEP to be the ones with the strict SPC structures. So the main theorem here is that so in this space, given this section, these spaces are in these whole spaces an open subspace in here. Okay, so it could only be just the subspace, proper subspace. And so in the corollary is that so U has the image here, then so in those cases, these will have a local homeomorphism to these spaces. Okay. Okay, so that's because we know that these are open local homeomorphisms, so it's just a restriction of these. So these open sets. Okay. So the let's go to the proper proof of openness. So so of course there's some similar work by Cooper, Long, and Tillman here, and but a little bit different. The techniques are a little bit different here. Okay, so basically the Kosovo-Bimbach function we recall is just so if you have a proper convex cone, so let's say B is the cone here, and then you take the integral of B star of these E minus X. So given X in the cone, you can define these functions, and this is a homogeneous degree n minus n minus 1. So this will be the metrics. So these are the Hessian metrics here. And so what we want to do is, so suppose we have some parameter of real projective structures, and so then we restrict this to any compact suborbifold. This is again a continuous parameter. So that means that you have this developing map in any compact subset of this universal cover is a family in CR topology continuous respect to the variable t here. So the definition 11.23 is a union is U be a union mutually destroying and neighborhood and mu0 and mu1 be real projective structures. And that be the extended developing maps. Then we say that these are delta cross in the CR topology in the compactation for if any compact path connected domain K mapping to overhead mapping to onto this, the associated developing map is delta cross in the CR topology for some C1 and C0. Okay. So this compact set, I should say, so this delta closeness, of course, depends on this k. So, but the k has to map onto this O bar. Okay, so that's the requirement. So maybe I should make that clear later. So OB strongly tame before satisfying IE and NA. So say you have mu0 with the general lens shape or speaker and Tn with affine suspension and mu0 has a Hessian metric. So n's are or T type. So if mu0 is SPC and then you have CR continuous parameter of projective structures, with this Rn T type preserved. And then let's say mu I Ti is some sequence converging to mu zero in CR topology. Then and for sufficiently small t, the affine suspension also of this mu t has a Hessian metric invariant, the group of dilatations. Okay, so we will obtain these things here. So we will prove this for Sn, and it's so we just want to obtain this Hessian metric. This step is to first we understand the enable deformation, and then we want to change the Hessian function on the cone associated with universal cover, and we obtain one for deformed and neighborhood by Hessian functions from the big function, and another one outside the union of neighborhood by isotopies, and we patch these together. Okay, so for we vary these two functions independently, but in the end we will, since they are very close, we can patch these together. Okay. So for A, we want to change the n, so we have some generalized Horosberg curve Tn, and the mu is continuous with respect to T for every compact things, and so we have some holonomy homomorphism bearing, and then so we cannot change R type to T type, but actually you can change to some radial n to radial n, and you could also have a radial n of general lens to the general lens, and the horospherical to a lens type or the horospherical ones. Okay, so that those things are all possible here. But of course, radial ends can change to horospherical end, but we don't need to consider that in the openness if we want to consider open properties. So nearby radial end is always radial. So and the next so two we want to change the totally geodesic ends. You can change to horospherical end and so on. Okay, so we can change lens type total geodesic ends to the lens type ones, or horospherical TNs to horospherical ends, or the totally geodesic PNs. Okay, so we don't need to consider lens ones becoming horospherical because we are just concerned with open label. So and then there are also finitely many ends anyway. So we kind of work with only one end at a time, and so we want to say the B is a end for this, and P prime is this, but we can kind of say this is B0 and B1, and BT the PN vertex for mu T, and HT and DFT be the holonom developing map and holonomy homomorphism. So basically we want to consider generalized lens type PN and horospherical N, and then so basically you look at the how these depth look from RB space of segments here, and then so AT be the space of segments passing some subset AT in the tilde depth or tilde or here. Okay, so AT is some subset of O tilde, so I didn't really write that. Okay, so those kind of thing. So we find some domain omega S0 approximating O tilde where this X, so S0 will be parameter. So we vary this for a fixed holonomy representation. So delta X0 is lens cone for mu0, so the boundary of this is the boundary of this. So this is a sort of a lens approximating the all of the O tilde. Okay, so I mean the double tilde, sorry, maybe you should say double tilde. So you have some lens-shaped Rn, and this top will be obtained by some CA lens. Okay, so the weight, so and then also this boundary is in the limit set of E tilde. Okay. So the basic idea to do that is to just make as many points as you want, many rays as you want, and then you can approximate these so that these Hassop distance is very small. Okay. Okay, so that's the only thing here. So you want to find these next the deformed ones, omega 0t. So this one acts on approximating this. I mean, maybe I forgot S0 here, and then so we denote by this sigma tilde et, the universal curve of end orbifold of the end with this mu t. So we are working on R type only here now. So you can always get these. Okay, so we obtain these domains, these compact orbifold. So the quotient will be compact orbifold, so the transverse to the radial rays. So then these you can find the compact hypersurface very close to original hypersurface bounding these end neighborhoods. Okay, and these will be again they bound the end neighborhood. Okay. So basically we want to obtain these kind of regions as we deform the representation, and so okay, and so we want to consider lens type case, and uh, right. So we want to consider the case when this is virtually abelian only. Okay, so why do I? Right. So other cases are very similar. So I don't. We only need to consider virtually abelian case because other cases will be uh, similar. Maybe I should see these. Right. So because I have to consider the horospherical, and I only consider the abelian case, but other cases are similar. Maybe I should say that clearly, but I didn't. Sorry. So where is now? I have to go back to where I was. Right, right. So you can take some compact domain here, and then you can vary this domain in this set. So this covers some fundamental domain, and so you can choose this to be very continuous with respect to t, and and then so the depth T partial gives you smooth inversion of this convex domain to the set of maximal segments in BT. Uh, with these vertices. Okay, so space of maximal segment. So these are actually you can consider these as a consider a tube, and then the set of maximal segments in this BT will be this domain. And so we have this immersion to the properly convex domain so that these are transversal. So if this is horospherical, then uh, these will be uh, depend on the using some Euclidean metric when it develops. Okay. Uh, and then you also have this condition that the boundary will be in the depth, these limit sets. Maybe there should be any depth there. Sorry, but anyway. So so basically, so you can approximate uh, these tilde using these, and right. So we haven't really selected this uh, boundary or till st yet, but we want something with this property here, and so the uh, right. So skip this. So the way to construct this is you want to look at this. Right. I didn't really approximate or tilde yet. I'm just constructing something like this. Okay. So I have this k in the compact set like this with kt perturbed ones. And if you look at the rays, this transverse rays mapping to here, so RT to be the so RBT is what this is so you look at only the things that are changed from KT, and then you look at all the union of these maximum segment from in this direction, and you take the intersection here. And so since this is very close, you can approximate those very closely. And the only thing that's not approximated is these ones outside here, okay, outside this RBT. But they are actually in the some epsilon neighborhood in the Hausdorff sense, because you can make this very small by taking K and KT very big, and you can assume that these are very small, and then so then you can consider that for every delta you can make these very, I mean every epsilon you can make it very small, smaller than this epsilon, this Hausdorff distance. So that's because you try to approximate within this k direction, and then these others are in a very epsilon neighborhood. So these are very thin in thin tubes in here. Okay. Okay, so those are the arguments, and okay, and then if you have a t and then you change to Horner-Spierker, and then the arguments are again very similar. You try to find these surfaces, and then so you use some supporting hypersurfaces near these boundary, and then show that their Hausdorff distance is again very small. Okay. Okay, so in the end, we want to get these kind of things, okay, very close to each other in Hausdorff sense. Okay, then also you can start with Horner-Spierker, and then you could change to the totally geodesic, and then you can also do the similar arguments. Okay, so for the Rn, I could do it for every case without changing, I mean, considering Horner-Spierker or not. Okay. So in the end, I get this kind of bound between these. And so now we come back to the proving 11.24. So we have some approximation like this, and then you can also get some diffeomorphism. So between these, so you can so in every compact set in CR topology, you can say these are uh, near the identity. Okay. So outside these n neighborhood, you can get these Hessian functions to be very close to the original Hessian functions. Then for ut, you can also look at these neighborhoods, and then so we take some compact neighborhoods and take the intersections between these and so on. And so the Hessian function restricted to these, and the other ones are going to be very close. Okay, so we can find these maps. So you find this partition unity, so that in this W it is 1. So B is some cutoff of the compact invariant neighborhood of the complement of U. So okay, okay. So so U is chosen very small. Okay, and then this P is 0 in the neighborhood here, and then P1 plus P2 is going to be 1. Okay, so you find this partition of unity functions. And also this FT very ratio is very close to 1 here. Okay, and right, so we find the Kosovo-Bimberg function for this O tilde, and this is and the Hausdorff distance between these are very close. Okay, so so there is this diffeomorphism, and so now you find the so new Hessian function for f prime t for this omega tilde omega ts, this one, this I mean this Kosovo-Bimberg function for this new one, and then you do the f tilde t is using this diffeomorphism, so it will be very close to the original f in any compact set, as long as we wish this to be very small. Okay, so that's the thing. And so you do this for each end. Okay, so you can do this for each end, and then you use this neighborhood, and then so you can show that they are very close here, and then so the phi t is the ratio between these two essentially, uh, but they are very close to 1, so you can assume this property. So you remove these, and then you add this back again, but now after being removed this, you do the partition of unity argument, partition of unity to get these two functions, and then this Vt is between these two numbers, and the derivatives of order 2 are sufficiently close to 0 by the small as epsilon because we can make this epsilon very small again. Okay, so P1, P2 are fixed, so you can, as long as you make epsilon very small, you can always get uh, these very close. Okay, so you see that these two functions are now we can be patched together. Okay, so so now we have a desired Hessian function close to the original one. Okay, so that's the Hessian part of the argument, and so once I have this Hessian function, then we can show that this result will have to be convex. Okay, so the so the convexity is just the function follows from the Hessian metric, and the reason is of course that So if you have any, if it's not convex, and there's a triangle which is embedded in this cone with one edge in the ideal set, and this length has to be, uh, but then you see that under this Jensen's inequality there, you get a contradiction. Okay, so the whole sec triangle cannot exist here. Okay. So therefore it is convex, and so that's how we prove that the things are open in this domain. Okay, I will take a 5 minutes break and then do the cross nets here.